All right, so we are back again, almost at the end of our conference. So now we're going to talk about blockchain testing. So blockchain is a pretty hot topic. For performance engineering, it could be quite a mystery to test a blockchain network. And also, I think blockchain is there's a lot of different framework, a lot of different stack. The KPI that we're measuring naturally in performance testing is obviously totally different in the case of blockchain, and that's why I've asked Antoine to make a session on that to give more makes things simpler for us. What will be what type of tests you can deliver in that environment? How can we generate load to make efficient and representative tests? I think there is different type of usage when it comes to blockchain, and the type of test will obviously change depending on the usage. This session will be presented by Antoine Toulme. So Antoine is the CTO of Whiteblock. Whiteblock, for those who are familiar, who followed the previous back, so he's working with Zach Cole. Zach Cole is the CEO of Whiteblock. Antoine joined Whiteblock a few months ago. He's more than 10 years of experience in multinational teams and enterprise and cloud and IoT projects. He is obviously an expert in developing and handling technical teams. He's worked with a lot of big names of the industry, and I think the best is to leave Antoine present his topic. And I'm pretty excited to have Antoine on board. Antoine, hi. How are you today?
I'm very good. Thank you for the introduction, Eric.
So where are you based today? Are you based in San Diego?
Oh, I'm based in San Jose, California.
San Jose, yeah, that's right. You're not traveling. You're not traveling today.
No, finally got a week at home. It's a relief. All right. Henry, can you see my screen okay?
I can see your screen at the moment. I think it's here I can see the slides. Awesome. So I'm going to mute myself.
Okay.
We won't interrupt your session. So
okay.
we will at the end of the session, we will have a dedicated Q&A where we can ask all of our questions. So don't hesitate for the rest of the attendees to drop your question in the Q&A panel. Otherwise, Alejandro Melendez is connected. Richard Mark Timpson has joined Alejandro as we speak. So you can go on stage and rock, do the rock and roll and explain everything.
Thank you. Well, thanks, Eric, for the intro. Hi, everybody. My name is Antoine. I'm CTO at Whiteblock, and today we're going to talk about testing blockchain. And to make it a little fancier, I'm going to call them distributed decentralized systems. And we're going to see how they are really close to what you would do on a day-to-day when you're doing network testing, but there's a little bit more that comes with blockchain. So let's go a little bit into that. First, I wanted to talk a little bit about Whiteblock. Whiteblock has been in business since 2017. We count many clients and partners across the industry. We work with Neotys a little bit, but we also work with the Ethereum Foundation, with the Enterprise Ethereum Alliance, among other things. And so we kind of seen everything under the sun in terms of blockchain, which gives us a unique experience and advantage when it's coming to talk about like new blockchains coming to market that want to test their blockchain in isolation with us. So today I wanted to first just reprise what Henrik was saying. We have new requirements for blockchain. First and foremost, all those notions of networks where you would be able to just peer, have VPNs, have some sort of control over the links, completely disappears with blockchain. Now we're pure peer-to-peer, we're across the planet. We will experience all sorts of really bad experiences when it comes to the internet. But the other thing is, beyond just testing the network, testing how the blockchain performs and how it reaches a consensus between the different actors so that we can actually assure that the same blocks are being agreed upon by all the nodes is really critical. And we call this consensus. So consensus has a very interesting characteristic depending on which blockchain you're working with. And most of the time, it means asynchronous behaviors, eventual finality. At any point in time, the chain can reorganize based on behaviors from different network partitions or different actors on the chain. And they relate on different mechanisms to ensure severe resistance to make sure that they agree on the blocks. Traditionally, proof of work is used. We also see a big use of proof of stake now with more modern blockchains, and I'll explain that in a bit more detail. On top of that, it's just not enough to talk about blockchain. Like all the infrastructures that is built on top also has significant bottlenecks in terms of performance, and oracles, bridges that connect different blockchains together become part of that architecture. And oracles, since you probably don't know blockchain, are systems that listen to blocks and are able to capture the specific transaction is being processed by the system. Therefore, they need to perform an action in return. Finally, I'll talk a little bit about new attack vectors, which are specific to blockchain, which are really giving headaches to everybody. I'll explain a little bit about how they look like, and we'll continue talking more about that in terms of future risks. So when we talk about blockchain, there's new KPIs, new metrics you need to capture as part of this. Everything from the data is transiting on a network, and we start with transaction size for this. We also want to capture who's sending transactions, who's receiving transactions. We want to actually see how much time it takes between the moment you send the transaction, the moment it's being propagated to the rest of the network. Right? So all those timestamps become really critical for us to see what we call down below here the block transmission time, the block propagation time across all the peers. All the information about the block. Block is made of many transactions, right? So it's number, of course, but also like its identifier, which is usually a hash made of that block, and the size of a block. Because of the size of a block, you may see different behaviors from the network in terms of speed, in terms of propagation. We'll also try to capture the size of what we call mempools. Mempools are simply on each node a unprocessed set of transactions and an unprocessed set of blocks. When you receive a transaction or a block, they will sit in there until we have the ability to process them. When we apply load, we'll see that those mempools tend to increase largely in size and may even become bottlenecks for performance. The block time is very important as well. So how much time does it take for a block to be produced by the network? The longer it is, the more secure the network is, but also slower in terms of transaction speed, we'll see. So for example, the block time for Bitcoin is about 10 minutes, and it's really, really long for you to make sure that your transaction went through, when the block time for Ethereum is about 13 seconds. And the block time for Ethereum 2 would be about 6 seconds. Then we capture a few more metrics which are really important for us because they measure the difficulty of just doing cryptographic checks on every bit of information that you receive. So just relating itself to the mempool size, we also see the time it takes to validate the block header, right? So when we just want to check that the signature of a block matches what the block contains. And we also have a big goal is to capture the time it takes to process the block itself. Especially when we run all sorts of smart contract operations, state changes based on the contents of a block. Those can take quite a bit of time depending on the implementation of the internals of the client. Finally, one that is dear to me is the anchor rate. The anchor rate is the number of blocks which have been produced at the same time as the canonical chain and are being rejected. The higher the anchor rate, the more difficult it is for the chain to come to consensus, and also the more waste we generate because we're propagating blocks that end up being rejected. So all those metrics become very specialized to blockchain, that they are really critical for blockchain to understand how it behaves, how it performs under load. So talk about that. We will be collecting those metrics that I just mentioned using logs, block data, and if we're lucky, for some of the blockchains, we now see the ability to use Prometheus or InfluxDB, this type of metrics being exposed directly on the client. All those tools help us, kind of get raw data from a test run, and then we would use data science tools like Jupyter, Grafana, the Elk Stack, Elasticsearch, Logstash, and Kibana to process all this data, make sense of it, actually provide results to our clients. What we've seen is that so far, not one run or one client has been giving us a standard. So everybody's different. Everybody's like a special sprinkle. Even between different implementation of the same blockchain, we see different log formats, different block data formats. So here, I'm going to talk a little bit today about the different types of testing we do. And I think right away, network testing is going to be very familiar to most of the attendees. And then I'm going to go down the list into less and less known test suites that we do, right? And we'll end with something that's very specific to blockchain. But first and foremost, I'd like to put you into familiar territory and talk to you a bit about network testing. Then we'll go into what the data looks like on a blockchain. How do you test for that? We'll talk about compatibility testing, security testing, load testing, consist testing. So let me not spoil that for you. I'm going to go into it right now. Network testing. So first and foremost, whenever we test something, we always first do a control group where we have the best latency, no packet loss, maximum bandwidth you can hope for. And we test all that in a fully controlled environment that we run for our clients. And it gives them the works on my machine feel, right? So we get the really optimal peak performance. From there, it always gets worse. So it's good to have this theoretical threshold by which we can actually measure the rest of our tests, right? The next test that we do is already specific to blockchain in a way because we apply latency between each of the nodes of the network. We start with 0, and then we start increasing the latency to see if we see a steep degradation of the performance. We always see performance degradation when we do that, obviously, because it's becoming harder and harder for you to propagate your blocks fast enough. It's a good warm-up. It's also cool because most of our clients come to us asking, well, I have a node in New York, I have a node in Tokyo. I'd like you to replicate exactly that geographical setup so I can see how bad things get if I add one more node in China or in France. So this gives us the ability to just like really give them an idea what latency is going to do to their clients. We then test bandwidth, which is another nice torture for them. That really depends on the client and the blockchain. So for example, for Bitcoin, bandwidth testing doesn't do anything to it because transactions themselves are fairly small. We're not talking about like large smart contracts being exchanged. On Ethereum, it will depend solely on the type of traffic we're thinking of, right? For Hyperledger, we can see large transactions easily being exchanged on network, so bandwidth testing becomes an easy bottleneck for us to point out. We also test packet loss. And packet loss doesn't really test the network itself. It's also exercising the client. Some clients will have to now resend messages asking for, I didn't quite get that block. Can you send that to me again? And sometimes we see catastrophic behaviors when you do that, especially some peers don't really like getting bad data and will start dropping other peers very easily at the drop of a hat. And that may actually trigger catastrophic behaviors where the chain starts degrading, where it's not able to get the data in time, or it's not able to keep peers alive long enough to get all the data they need. So we also combine all those things together, and that gives us the idea of a network stress that really replicates what a real internet peer-to-peer network will feel like. What's really interesting with blockchain is that you don't really get to choose who you peer with. So even though you may have 3 nodes next to you, you may want to also peer to that node on the other side of the planet because it gives us a bit more independence. And otherwise you may fall under some sort of attack when you're only talking to local peers that may influence you. So those gives us a very realistic snapshot into the behavior of the test net of the network on the real internet. We also test different topologies. So ideally, when you start testing, everybody knows everybody else. That's great because it gives us a good baseline. Now let's torture that a little bit. Instead of having everybody connected to everybody else, we can now connect you to just 2 peers out of 10. that will actually stress test the gossip propagation of all those blocks, all the data that is required on the network. We can also go as far as doing an actual sequence, right? Each peer knows the next, but there's no way for them to connect to each other outside of that sequence. That also gives us like some pretty long propagation time and an idea whether this is even like a suitable configuration. Here, the block propagation time becomes like the variable you want to really look for, and it's deeply affected by this type of topology. A twist on that is to move to a discovery topology testing. Most blockchains out there actually do their own discovery. By that, I mean that you would initially connect to a first node that gives you access to a number of other nodes on the network from which you would, select a few to peer with. Ideally, the topology of that network is as good as it's going to get, right? Close to perfect. But we need to test that assumption, right? Because it usually requires them to mix up some different IP schemes to have a good masking mechanism to choose which peers to connect to. Most of the blockchains out there use some level of academia bucket routing, where you're going to use the identifier of the node, and based off that, you will select which bucket it's on. And if the bucket is full, then you don't even try to connect to that peer. So sometimes you can actually see abuse scenarios where those buckets are filled the wrong way, and we'll talk about that in a second. Those topologies need to be tested as well. So let's go to data testing now. And data for blockchain is mostly, of course, block data. The first thing that we do is we try to see how long it takes for a new node to join a network. There are some tales out there that it takes a long time to synchronize with Ethereum, and those tales are actually true. Here is some Twitter post from a user who's been trying to, for 25 days, sync up the whole chain. You can see that the size of the blockchain at the end of the exercise is about 195 gigabytes, which is not that big per se. But the problem has been that during those exchanges, a lot more data is being exchanged. And you can see that the biggest factor right now is the disk I/O for that person. So this is very interesting for us because we're seeing that the bottleneck is not always just the network, it's also the inner to the machine and how much time it takes to process all the data in there. We also do smart contract testing. So we will actually deploy a contract. We will test it out by sending a bunch of data just to exercise it. And we'll see that the contract has to deploy and to execute a certain way. We'll also be able to test the infrastructure that depends on that contract. So I was talking earlier about oracles. If you have any listener that is supposed to perform an action, such as sending an email, refresh a website, push to Git, all those things get tested at the same time with us. This is very specific to blockchain. It's really tricky, and it depends on each different platform. Another thing that we've been doing very successfully in the past is to test different implementations. So we would be taking 4 or 5 different clients, and we'd be testing if, given the same data and the same block data, we see the same output, and we see that they reach consensus. This is done routinely by each community around the blockchain for each what they call hard fork, where they have a change of behavior, and they need to make sure that everybody is performing exactly the same. So we've seen that, for example, with the last Constantinople testnet, where parity started behaving a very different way. The issue was so small. It was just that they were using unsigned integer instead of using a signed integer to issue refunds on a particular ops code deeply inside the Ethereum virtual machine. So the virtual machine that executes contracts for them. By having this issue for the first time with that hard fork became a problem because sometimes the refund could be negative. So we saw that different clients could not come to agreement on the output and the behavior of the blocks, and we're starting seeing forks inside the testnet itself. Security testing. That's very interesting for blockchain because those vectors are really different here. I was mentioning earlier that blockchain performs its own discovery. And when they do, you can actually take kind of advantage of that. If you connect to a bad boot node, initially. They may feed you peers that will behave a certain way to make you think that you're on the right chain, of course, but it happens to be the chain that they care about, and you can actually have those clients being customized to only accept a specific transaction that benefits a bad actor. So if you were to do that, you need to have a number of protections placed inside your client to make sure that first, of course, you want to have more than one boot node, but also that you won't be listening to peers which are in a specific IP range only. Otherwise, you may fall prey to an Eclipse attack. We also test double spend. Double spend is one of the biggest claims to fame of Bitcoin, which is if I was to send you, let's say we have an account on the chain and I'd like to empty that account, and I'm going to send you two conflicting transactions, one that says send all the money to A and one that says send all the money to B. With Bitcoin, what you do is that you have enough time between blocks for proof of work to ensure that the transaction cannot be, the second transaction cannot be executed. It would be rejected as part of that. But some chains don't do that. Some chains have a very different behavior with there. So EOS is different. Proof of stake chains will be widely different. They rely on different mechanisms for security, such as ordering transactions, using an orderer, like Hyperledger would do, or using the medium timestamp time from just like Hedera, try to order the blocks in a way that it cannot be altered and to make sure that only one transaction gets in. 51% attack, also a valid claim that's been happening with Bitcoin and Ethereum for the longest time. If I control the majority of the nodes of a network, then I can make it do anything I want. I can actually reject all the blocks I don't like. I can even just produce my own blocks and just keep going on my own. But some chains now actually support up to 2/3 of the nodes being attacked, such as Polkadot. If2 would probably be in that camp as well. The idea is to reconstruct that attack, modify the node so that they only follow a chain built on top of a specific block that we choose, and see if the chain is able to survive this. At worst, we'd be looking for a chain that would still be able to function, but the consensus algorithm wouldn't be blocked until the situation is resolved. And notably, Ethereum and Bitcoin are both vulnerable to 51% attacks today. In terms of load testing, everybody does load testing. I'm not going to teach you much about that, but for blockchain, we have a twist on it. The first thing we do is that instead of doing load testing blindly, we try to test one node of the network. The idea is to load it up with thousands of transactions per second for minutes at a time. Then we'll be looking for all the OS stats that we care about, such as CPU usage, memory usage, of course, the size of the mempool for the transactions, and we'll be looking at the other nodes on the testnet. Are they able to really use those transactions? Are the transactions even being dropped, or are they successful? And finally, we want to see how far we can take it until the node falls over. So once we have that, we move to the distributed load testing. We actually will inject load on every node of the network, and we'll try to see how fast we can get the network itself to kind of resist and reflect and maybe even retaliate to that level of transaction load. So for example, for Ethereum, if you were to start injecting a number of transactions per second, the gas price of sending a transaction would go up as a result, because it becomes harder and harder to pick which transactions to pick from. And it would be easy for miners to say, well, I'm only going to take transactions over a certain threshold, and to start setting a higher and higher gas price. This happens on mainnet right now, today. The gas price has been going up and up because the Ethereum network is seeing more and more use. Consensus testing is now we're hitting the core of what we want to do with blockchain. First thing that is really important for everybody is to make sure we can get a good block time for blockchain. This is just as important as seeing how many transactions we can digest per second. Most blockchains try to go for something like a constant block time. If you're proof of stake, then your block time is actually constant, and you need to be able to propose a block within that time slot. If you're using proof of work, then you're block time is actually kind of fleeting depending on the difficulty of the algorithm that you apply to it. But the difficulty itself needs to be adjusted as the load increases to make sure that the block time is able to stay constant. So if there's less and less miners and less competition for blocks, the difficulty would go down. If the more and more miners are trying to propose a block at the same time, then the difficulty will have to go up to keep the block time constant. This is very difficult math. It involves GPUs. It involves quite a large testnet. We also do state transition testing. We've done that 2 weeks ago with the Ethereum 2 community. What we want to do here is for nascent blockchain that's not being deployed yet, we want to make sure that we're able to, some of the pure math. We want to just take an existing state, apply specific change to it, and make sure that across all implementation of that blockchain, we see the same result, the same state being exported by the chain. So this requires quite a bit of tooling in terms of being able to see the state, generate initial state, export the state in a way that can be diffed against what would be expected, but it gives us a very high bar in terms of compatibility between clients. Also, finality testing is really interesting. So I mentioned before, clients will eventually declare that a block is final after a certain amount of time, either because a number of blocks have been built on top of it, and it's unlikely that a reorg would happen and that chain gets moved, or it's a proof of stake chain, in which case it's completely deterministic, and you can actually make sure that 2-3 blocks in, the block can be considered final. But clients differ, even their implementations differ. So you may see different clients behaving quite differently in the ways they declare a block final. You could even tune that a little bit to be a bit more on the risky side. And it's interesting because the moment a block becomes final, then you can also do all sorts of things with the data in that block. Before that, it's not really useful. We do a lot more testing. A lot of our clients come to us with custom testing cases that, frankly, we have to pretty much go off the grid and just do that on a case-by-case basis. One popular demand has been that compare me with Ethereum, compare me with that other blockchain, right? So we have a completely different way of executing transactions or executing the state of a blockchain. We'd like to make sure that we're able to get the same level as what Ethereum provides, for example. We also been testing with network bad actors, notably when we were working with EOS. What happens if you have a node that is similarly, good node, but at some point stops following traffic, starts spewing bad messages? Is the network able to resist that? Is there any sort of cryptographic check being made on the exchanges between the different nodes? We also see different topologies which are a little more specialized, such as for LibP2P, the use case where they use rendezvous nodes that allows them to have a centralized point of contact between nodes. This is going to the next point, allowing TCP hole punching. So everybody can just connect to one central point and then the connection is made between actors. However, it's a huge centralization pain point that can be attacked very easily, DDoSed, taken down, all you want. We see some novel approaches now to traffic using UDP. Quick is making a lot of people rethink how they could maybe use UDP for those things. Of course, UDP itself is very interesting technology, but it's not giving us all the acknowledgement, the live transaction. It's not we can't use it as a two-way stream. But I think we're going to see more of that over the years now. And kind of to expand on that, all the UDP traffic ends up being on top of Tor, all the WireGuard VPN that use UDP under the hood. So we're playing a little bit with Tor and VPN to see what's possible, how things work. So I think we'll have more on that in the coming year. And I mean, my list is falling short. We have many more custom use cases that come up to us every day. So that's it for me. I think I covered my main points, and I'd love to get some questions if you have any.
All right, thanks, Antoine. I have a few questions, in fact. So let me put all the different speakers up. Here it is. Oh, no. Okay, he's probably discussing something, mute himself. So one of the topic because I discussed with one of our partner, and they said so they've been doing load testing for, let's say, for a bank, and they were using RPC testing. And one of the thing, and I think you resolve it, so tell me if you it's the case. They were saying that because of the data you mentioned, you're mining the data, you're preparing an environment. So they basically took some AWS instances. They set up the environment, they did the test, and in fact, during the entire project, it was not able to tear down the instances because they will lose the data. So at the end, the cost of the test was not especially related to the building scenarios and running tests. It was more about maintaining those cloud instances during, let's say, the entire project time. So at the end, they had a huge cost related just to host the testing environment. Yes. And I'm pretty sure that you can resolve that point. Am I correct?
Yeah. So that's a valid concern, and we see that a lot with testnets. Over time, they aggregate a lot of data, and it becomes really unwieldy. What we have done is we completely built a product for us to be able to isolate a blockchain into a fully controlled environment that we run for people. And in some cases, not always, some folks want us to test against the real data of the blockchain. So recently, we had a customer like that where we had to inject the mainnet state into our instance. So we're kind of lucky because when we do this type of test, we try to keep them as short-lived as possible, and we have backups of that mainnet state that allow us to just perform a restore, if you like, and then sync up the rest of the nodes to that mainnet state. So that shortens quite a bit the cycling of testing. If we were to run long-lived nodes, we would be spending quite a bit in cost. So the idea is going forward, we're going to make that even more parallelizable, where it's easy for you to just click a button and have a bunch of environments being generated on the fly. We try as much as possible to not have to deal with the data on the test itself. I would say though that for an average test case, we see 2 to 3 gigabytes of data per test. So all the tests I mentioned, even the latency test, would generate 2 to 3 gigabytes of data to parse.
And the other thing, what I thought was painful, because I worked closely with you guys to implement support of all the frameworks that relies on Git.
Yes.
That's one face of the iceberg. And yes. What I think which is painful is there is so many different framework and way to deliver it. So it means if you switching from, let's say, Pantheon or Ethereum to Hyperledger, then basically all the process to run the test is totally different. So you have basically you're continuously adapting and building frameworks to make sure that you're able to test everything. So I think from my perspective, it seems an awesome technology, but quite a bit expensive. As we speak now, because there is so many different frameworks. So I think you're supporting many frameworks on the market, but I guess it's impossible to predict which ones will be more important than the others. Could you basically share with us what type of framework are currently used and make sense to invest?
Sure. So we support over 20 different blockchain protocols. The main one, the flagship one, would be Ethereum. Ethereum is actually, you get lucky with it because they use JSON RPC, which is not really standardized very well, but good enough API to do any sort of load testing and also to request data back. There's another few ones that are really important, especially for the enterprise. You mentioned Hyperledger. I would also add to that Quorum, which is a fork of Ethereum. It's ever so slightly different, but it's mostly behaving the same. We have some good hopes about Ethereum too. We also see some interesting research in Polkadot. I would say that this is worth looking into. In terms of permission networks, of things which are more on the private side, so they're not open networks where anybody can join, but they control kind of how many nodes are in there. R3 comes to mind. Hedera is kind of interesting as well. They have a nice architecture. That would be kind of the type of clients I would look at. And so to kind of also answer your questions, the way we've been going about it, and I think this is going to be kind of a pattern for us going forward, is that this is the first question we ask our clients. Do you have a load testing tool? And actually, most of them say no. They didn't think of that. They don't understand. We have to actually educate them, because it's not just a simple sending request. It's not JMeter. You're not sending the same request over and over to see if it can take the load. Instead, what you have to do is that each transaction has to be slightly different, has to be bound to different accounts. Between accounts, sometimes transactions are identified by an announce that lives on the sender accounts. So they have to be incremented or have to be random between them each other. And you want that to be distributed across all the nodes. So each node is going to have a different set of accounts. You're going to have to work with all of that. And in general, this becomes a very complex exercise. So what we're trying to do now is to front load that right away in the discussion. And we always start that discussion with that people. And they completely understand that about 10 minutes in, and they understand the value they could get from having such a tool pretty quickly.
All right. Alejandro, you're connected. Do you have any questions for Antoine?
Not that I can think of. There were very good questions being asked.
All right. Thank you.
All right. So Antoine, thanks again for your presentation. For those who's, so we only have a few people left connected. So in any case, your presentation will be available on our website.
Absolutely.
And I think if we publish a blog post, it would be great to list the framework that it supports. I think it would be meaningful.
I look forward to this. Thank you so much, Henrik, for hosting this. This is a great event, and I look forward to more.
All right. Thanks, Antoine. Have a great end of the day.
Thank you.
Now we are taking a small break before we start the session with Alejandro, and then we have Mark that will finish the conference. All right, so let's take a short break. Thanks, Antoine, again, and see you in 15 minutes. No, more than 15 minutes, because we're a bit ahead.
20 minutes.
So let's say in
20.
in about 20, less than 20 minutes. All right.